I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless this time, Lord. In your name I pray. Amen. So you guys have questions about the mission, perhaps? Yes. I have things open, but they're all the wrong thing. I see here. So I need to. So we're on mission 7, right?
8.
Oh, 8. Yeah. How soon I forget. Ooh. Hey, this one's got nice problems. Beauty is in the eye of the beholder, I suppose. Let's see here. It's really only true to a certain point, though. You know, otherwise commercials wouldn't work. All right. So what was the, what do you guys want to know about?
Well, you see, the first one.
The first one.
Yes. So, like in the basis, we're already given 3 out of 4.
Uh-huh.
So, are the first 3 already in the form of the prime?
I guess that's the question, was I nice to you? Did I already start you out with 3 vectors which are pairwise orthogonal, all of length 1? I mean, looking at problem 127, those first, like 1131, what's the length of 1131? It's 1 plus 1 plus 9 plus 1. So the length squared is 12, square root of 12 is its length. So that's been normalized. And the same for the second one. And the third one, those are all unit vectors, is my point. The division by root 12 or root 6 makes them have length 1. If you take the dot product of the first 2, you get what? 1 minus 3 plus 3 minus 1, you get 0. And so it looks like I started you out. I mean, I've given you 3 vectors which are already orthonormal. How do you find a fourth? So this goes back to a more basic question, right? So let's think about some theory. Some theory will make your life easier here. If we have W is a subspace of Rn, right? Then W direct sum W perp is equal to Rn, right? So if you think about this, if you think about W as being the span of your first 3 vectors, v1, v2, v3, right? In problem 127, think about the first 3 vectors. Then that is 3-dimensional, right? And I guess what I'm trying to say is you're really just looking for one additional vector, right? You're looking for the whatever it takes to span the perp to W. It's one way to look at it, right? Now, one way you could do this would just be to, I mean, there's a lot of different ways to find V4 strategies. Here's the true strategies I see. 1, V1, V2, V3, let's say V. You just need to find something here that's, not, if it's not in W, right? If whatever you put there is not in W, then that means that that's a linearly independent set by the plus minus theorem, right? Because V1, V2, V3 is linearly independent. So if I join a vector outside the span, it's linearly independent. And if that's a linearly independent set, then I can apply the Gram-Schmidt algorithm on this, and that will change V into what I want it to be. The Gram-Schmidt algorithm here is really boring up until the fourth point because it doesn't do anything. V1 is V1 prime prime. V2 is V2 prime prime. V3 is V3 prime prime. So if we could figure out what V is, we could just run, V4 prime would then be what? It would be V minus, V dot V1, V1 minus V dot V2, V2 minus V dot V3, V3. And then I'd make V4 V4 prime divided by the length of V4 prime. That would give me the fourth thing I need to make beta an orthonormal basis. That's one way you could do this. But what's the starting point? You got to figure out some V. My phone keeps doing this to me. But you aren't in your office. Second. What room are we in? I'm in DeMoss Hall, 2052. Were there other people at my office?
A scary lady, but she left.
A scary lady, but she left. Okay, all right. You're welcome to come in here and ask it.
So you're doing a whole session?
Yeah.
Oh.
I'm sorry. So sorry.
I'll leave.
Okay. Aw.
I was going to ask you about this, so it's not
Oh.
quick questions.
It's not what?
It's not quick questions.
Oh, yeah. I'm sorry, Emily. Okay, so one way we could do, but you got to find V not in W. What's the strategy for that? You're looking for a linearly independent set of 4 vectors, right? So you just guess, just pick anything. It's almost going to work, as long as it's not a linear combination which you already have. I usually start with unit vectors, like the standard basis. I think, like is E1. How would I check if E1 is not in the span? Somehow, after I did the talk to text, and it has changed what I said into Ave Maria. How did it get Ave Maria from what I said? That's, wow. But I like the talk to text. It's hilarious. It's okay. Okay, so I hope you see that this approach will work. I mean, but it's kind of a little bit awkward. It's a little clunky because we got to start by finding a vector we don't, we have to guess. There's another strategy, which is to just find basis for W perp. That's actually a straightforward calculation. That's another approach we could take here. How would you do that? So W perp, right? It's the span of V1, V2, V3, the perp of that, right? But we proved that that's the null space of V1, V2, V3 transposed, right? You take those vectors, you stick them in a matrix. Well, you take your vector, your column vectors, write them as rows, and find the null space of that. It's going to be a one-dimensional null space that will give you the direction of V4, and then you just got to normalize it. That's the easiest way to do this, I think.
Because I was trying the other way.
Actually, that's not true. There's another easier way. You just calculate the determinant of E1, E2, E3, E4, V1, V2, V3. It's the triple cross product. if you have 3 4-dimensional vectors, you could find a fourth which is perpendicular to the original 3 using this formula. But this is just dark magic
Okay.
that I happen to know.
So we should do find
You should do the middle one. The middle one's the middle one or the first one's the most healthy way to do it. But it's fun to notice that you could do it that way. In 3 dimensions, definitely in 3 dimensions, cross product's a good one. Right? If I've got V1 and I've got V2, and then I say find something that's perpendicular to the first 2, right? The cross product not only gives you a perpendicular vector, it gives you a length 1 perpendicular vector. If you already have 2 unit vectors, if V1 and V2 are already unit vectors. Like, for example, in your usual notation, I hat, J hat, and then if you put over here I hat cross J hat, well, you guys know what that is. It's K hat, right? So that turns out that generalizes. If you have like n minus 1 vectors in Rn, you can use this. Okay, I shut up. Other questions? You're not.
Is there a certain way that we're supposed to know how to calculate the perp, or is it just something that we should?
What is the, yeah, you should know what the perp is, and you should have calculational strategies for how to find it. But W perp, right, is x in V such that x inner product W is equal to 0 for all W in W. So it's a set of vectors which are perpendicular to a given, well, it doesn't even have to be a subspace. You can calculate the perp of like one vector. So this is the cool thing about perp is if I calculate, for example, if I'm in like R3, right, and I said, what's the perp of E3? That would mean, you know, x, y, z in R3 such that what? X, y, z dotted with E3 equal to 0. I mean, here, for all W just means E3, because that's all there is. And what is that? Well, that's z equals to 0, right? So I think it's important to have a geometric picture of what the perp is, right? Like E3 is just this, right? But the perp to E3, it's the set of all vectors which are perpendicular to E3, which as an equation is z equal to 0, but, you know, we could think about that as being, you know, the xy plane in this particular context. All right. So you asked me, how do I calculate it, right? The tools we have at our disposal, there's a few tools we have. The one tool we have is that the direct sum of W and the perp is the whole space, right? So one of the things that's nice about this is if you can find a basis which respects the decomposition, like if you find a basis for all of V, and part of your basis fits into W, right? Then whatever doesn't fit into W must be a basis for W perp. They're complementary. It works like that. That's one thing that's kind of helpful. You can use the projection idea. Like we can find something. There's so many things to say here. So many things to say. Every x can be written as like x1 plus x2 for this one in W and this one in W perp, right? I mean, there's that unique decomposition. That the fact that that's possible is sometimes useful. If W is the span of beta 1, let's say, then x1, and if this is orthonormal, then we can calculate x1 by the sum, whatever dimension this is, say I equals 1 to n1 of x against vi. Like this will pick out the projection in the W direction of x. We can use the orthonormal basis to calculate project like that. So if you have an orthonormal basis for your subspace, you can do all kinds of stuff, right? All right. Going back to the thing I often ask about Rn. If you have S as a subset of Rn, then S perp very conveniently is just the null space of A transpose, like that, S transpose rather. Oftentimes, that's the thing you want to use to do a problem. Want me to show you specifically one of these? I'll make it easier than your first homework problem. So if we had like S equal to 1, 1, 1, 0, 0, and 0, 0, 1, 1, 1, just to keep the math somewhat easy here, then to find, suppose I want to find a basis for the perp to S. What would it, S perp would be what? It would be X in R5, right? Such that X dot, let me call this thing V1, let me call this thing V2 for the sake of not writing them again. So X dot V1 equal to 0 and X dot V2 equal to 0. If I have both of those conditions, that's what it means to be in the perp. One of your homework problems was to prove that the perp is a subspace, no matter what S is. Even if S is not a subspace, the perp to S is a subspace. And the perp to the perp is always the span of S. S perp perp. That's something that's true. If S already happens to be a subspace, then the span of S is just S again. All right, but anyway, let me focus here. How would we act? But the way, what these equations mean, you're looking really for the null space of 1, 1, 1, 0, 0, 0, 0, 1, 1, 1. So what I did was I took the column vectors and I transposed them to make rows, and we just need to find the null space for that. The null space for that will be the perp to S. So how do we calculate null space? Well, you guys know, right? So let's see here. This is equal to the null space of 1, 1, 0, minus 1, minus 1, 0, 0, 1, 1, 1. So what I did was just one row operation. I subtracted row 2 from row 1, and then I'm already done. Right? That's in the rough. So, okay, I'm going to go over here. I'm going to say, okay, so that means that, like, x1 is equal to minus x2 plus x4 plus x5, and x3 is minus x4 minus x5. So, and of course, here, x2, x4, x5, those are free. Those are free. And we expect that the perp is three-dimensional, right? Because it's complementary to S. Was it?
No, I got it.
You can, I mean, this is for you. You guys can stop me. I really don't mind. All right, so this is the span of, let's see here. Let me do the calculation off to the side. So we've got x1, x2, x3, x4, x5, which is equal to, in this context, what? Minus x2 plus x4. Oh, poor planning on my part. If you don't mind, I'm just going to write down x equals to, x1 is minus x2 plus x4 plus x5. x2 is equal to x2. x3 is minus x4 minus x5. x4, well, that's x4, and x5 is x5. That's a typical point in the null space. So we can factor out the parameters. x2, right? Minus 1, 1, 0, 0, 0, plus x4, 1, 1, 0, minus 1, 1, 0, and then plus x5. I can't write down here. 1, my handwriting slowly but surely decays as you get further down the board. Thank you, negative 1, 0, 1. All right, so it's the span of, and I'll go vertical here this time, minus 1, 1, because it's convenient, 0. So that guy, and then 0, minus 1, 1, 0, that guy, and then this guy. 1, 0, minus 1, 0, 1. So if I call these things V3, V4, V5, are those orthogonal? No. Like V3.V4 is not 0, and V4.V5 is not 0. So if I wanted to turn that into an orthogonal, like an orthogonal basis, I'd have to run Gram-Schmidt on it, you know? So but set that aside for a second. This is a basis for the perp to S, you know? I mean, these are not, how would you take V1 and V2 and make it into an orthogonal set? We'd run Gram-Schmidt, right? So like V1 prime prime would be what? Yeah. That. And then what would V2 prime be? V2 prime? Yeah, V2 minus what? V2 with V1 prime prime, V1, right? Which would be 0, 0, 0, oh, 0, 0, 1, 1, 1. And 1 over 3. What's the dot product of like V2 with the, ignoring the fraction in V1 prime prime? If you just take the dot product of these two, you just get the 1 in the middle. That works out to 1. And then anyway, if you do this, you get this, I think. So by my calculation, V2 prime would be minus 1/3, minus 1/3, 1 minus 1/3, which is 2/3, and then 1 and 1. I recommend if you find yourself with this kind of thing in the homework, what you should do is not, like if you just do the algorithm I gave you without thinking, you would then normalize this, right? But that would be calculationally foolish. What you should do is factor out the third, then normalize. In the following sense, like this is 1/3, minus 1, minus 1, 2, 3, 3, right? And so here's the fun thing, is V2 prime prime is just 1, minus 1, minus 1, 2, 3, 3, divided by the square root of 1 plus 1 plus 4 plus 9 plus 9. See, I can completely ignore the 1/3. If you want to normalize a vector, right, think about this. If you're normalizing a vector, if you've got a scalar multiple in front, it doesn't matter. Because a scalar times the vector is in the same direction. So just ignore the scalar and normalize the vector. That gives you a unit vector in the same direction. And you don't have to do anything with like adding thirds, which is obnoxious. And so whatever that is the, so 1 over root 3, 1, 1, 1, 0, 0, and then minus 1, minus 1, 2, 3, 3 over the square root of 24, huh? Hey, does the dot product of that vector and this vector work out to 0? Look at it. So you get minus 1 plus minus 1 plus 2 plus 0 plus 0. So you get minus 2 plus 2, which is 0, all divided by the square root of 24. And they both have length 1, so there you go. V1 prime prime, V2 prime prime are orthonormal. That is an example of a reasonable Gram-Schmidt question for a test. On occasion, I'll ask you guys to run it on 3 vectors, but it does not give me joy to grade those. unless they're particularly simple vectors. Even so, horrible. I shut up. I take a breath. You guys have questions?
So just to make sure I'm thinking right,
Mhm.
find the null space, you just have to row reduce it?
To find the null space, we row reduce to the reduced row echelon form, then we look at the equations that correspond to that, and that tells us which are the free parameters, and then we factor those out. The vectors which appear next to the free parameters are a basis for the null space. So if the rank of the matrix plus the number of free parameters in the null space should always be equal to the number of columns. This is rank nullity.
So could you have, instead of using x1, could you have also used x2?
I wouldn't advise it.
Okay.
This is this. I mean, you could here, but I wouldn't advise it. This is the standard null space basis. Now, if your reason for using x2 was to try to get a like perpendicular basis for the null space, I'm fine with that. If that's what you're thinking about, okay, fine. But this is our standard technique, is to use the non-pivot columns as the parameters. If you don't use non-pivot columns as parameters, if you use pivot columns and non-pivot columns as parameters, if you're unlucky, you'll choose two parameters which are not independent. And when you do that, then you're in trouble. Using non-pivotal columns variables as the free variables in the solution set forces independence of those free variables. That's why we do this. So it's just dangerous to do other things. Not impossible, but dangerous. Other questions? I know you guys have other questions. I'm going to erase this. Can I erase? Yeah. The last part of problem one was to find the coordinates with respect to beta. How would you do that? Once you find that V4, right, you can just take the dot product with the given basis, which is orthonormal, and the dot product of the given vector with that basis will give you coordinates, as we discussed. For example, if I had one square root of 3, right? And then say suppose we had that. All right, I'll just stop there. I don't want to. Finding the third one is a pain for me. So I'll call that beta. All right. And you could look at W equal to the span of beta. That would be a what? Subspace of R3, two-dimensional. Then we could play the following game. We could say, okay, so W is like this, right? And my question is, will you give me any point in R3? I'm not really sure what W looks like exactly. I'm just making something up, guys. This is just a sort of a generic picture. So you guys give me any point in our R3. 1, 2, 3. Perfect. Oh man, look at that. Maybe this is 1, 2, 3, okay? Do you guys know how to find the vector which is like parallel versus perpendicular? So this one would be what? The projection onto W of 1, 2, 3. And the other one would be what? I called it orth, right? Orth W, 1, 2, 3. How do you find the projection onto W of 1, 2, 3? Do you know? The same as I do it in Calc 3. Yes. But I don't do this in Calc 3 that much. I mean, usually we talk about the projection of a vector onto another vector. Right, but that for a vector onto another vector, right? Not for a vector onto a plane. It's different and yet the same. So the way you do it is 1, 2, 3 dotted with V1 in the V1 direction plus 1, 2, 3 dotted with V2 in the V2 direction. What this is that those dot products select the part of 1, 2, 3, the component of 1, 2, 3 in the V1 direction, the component of 1, 2, 3 in the V2 direction, and then they put it in the V1 and V2 direction to put it together. What do I mean by V1 and V2? I'm talking about these guys up here, right? Like these are, this only works if V1 and V2 are orthogonal and normal. But they are, so we can do this. So what is that? So I usually just square the one, that's like 1/3. And 1 minus 2 plus 3, 1, 1, 1. This would be 1 minus 1, 1. 1/2, 0 plus 2 plus 3, 0, 1, 1. I just take the normalization factors and put them out in the front to make the calculation easier. What's that? 2? 5? No. Yeah, 2/3. 2/3, 1 minus 1, 1. What's that work out to? 5/2. 0, 1, 1. So we've got 2/3 minus 2/3 plus 5/2. And then 2/3 plus 5/2. There you go. That's the point. That gives us this point right here. It's the point in W which is closest to 1, 2, 3. If you want to define orth, what do? I mean, orth is just, it's just 1, 2, 3 minus the projection. The difference in Calc 3 is you just got one thing you're projecting on, so you just do this. You would just have the first term. You wouldn't have two terms. Like, for example, if you had 1, 2, 3, and you're projecting onto the x-axis, let's say, then the projection in the E1 direction of 1, 2, 3 is what? It's 1, 2, 3 dot E1 times E1, also known as E1. But if you have more directions you're projecting on, you just take the sum of the projections onto each piece and build it together. Yeah. You guys can ask me a question, otherwise I'm going to just keep doing this. Make me tired. Quiz, you know what a quiz I almost gave? I was really seriously thinking about giving the following quiz today. Today, yeah. I almost gave you guys the following quiz. I mean, I'm not kidding. I was really on the cusp of giving this quiz today. Find line closest to points 1, 2, 2, 3, and 0, 7. Do you know how to solve this problem? So this was in the video that, not this problem specifically, but this idea was in the video. This is a least squares problem. So what is a line? We're looking for y is equal to like c1x plus c2, right? That's our model. So our goal is to find c1 and c2. So we do 3 points determine a line? No. 3 points over determine a line. So the odds are pretty good that these 3 points are not on a line. But you plug them in to the model, what does it give us? It gives us 2 equals to c1 plus c2, right? We get 3 is equal to 2c1 plus c2. We get 7 is equal to 0 times c1, right? Plus c2.
Is it bad just to say C2?
Hmm?
Is it bad just to say 7 equals C2?
Oh, no. It's fine, but it's just, there's no solution here. This is an inconsistent problem. So all we can do is take this problem and trade it for like the following 1, 1, 2, 1, 0, 1, c1, c2 equal to 2, 3, 7. So I call this thing, I don't know, M, and this is MC equals to, let's call that other thing B, That's an inconsistent system. There's no solution. All right? 2, 3, 7 is not in the column space. Does 1, 2, 0, and 1, 1, 1. I don't believe. Right. To get the 2 and the 3, add the first 2 rows, fine. But when you do that, you don't get a 7. So we're out of luck. Now, to find the solution, you don't find the solution, but to find the best approximation to it, what I proved in the video, right, is that we multiply by the transpose. M transpose MC is equal to M transpose B. The solution to this corresponding normal equations, right? The solution to the normal equations gives us the best fit approximation to the line. In the same sense, you talk about regression in statistics. That optimization procedure with partial differentiation and all that yields the same thing. So what is M transpose M? Can you guys calculate it for me? What does M transpose M equal to? I mean, the big picture is the 2 by 2 matrix, right? What kind of 2 by 2 matrix is it? Is it symmetric or anti-symmetric, or is it neither? I think it's symmetric, right? Ooh, hey, that means it's orthonormally diagonalizable, although that's not terribly relevant to this problem. So M transpose M is that, whatever that is. And what's M transpose B equal to? So what do you guys get? Can you work it out? 5, 3, 3, 3. And this one? 8, 5. All right, so look at that. Now we're looking to solve 5. The normal equations are actually this: 5, 3, 3, 3 times, C1, C2 equals to 8, 5. How would you solve that? 2 equations, 2 unknowns. However you like, right? I personally prefer to solve it by multiplication by inverse. So multiply by the 2 by 2 inverse. I get 1 over 6. 24 minus 15 minus 24 plus 25. 9/6. 1/6. Therefore, y equals to 9x plus 1 over 6. This is the line which is closest to those 3 points. If I haven't made an arithmetic mistake, which would be amazing. So less important than hurrying through the details is understanding the big picture of what we're doing here, which is if we have an inconsistent system, we write down the equations, right? Then to find the best approximation by least squares, we multiply by the transpose of the coefficient matrix and solve those problems, solve the corresponding problem. And that's it. That's the method of least squares. So now, I wonder how many people would have got that quiz today. Because I wonder how many people actually have watched the video. At least 5 of you, right? Yes.
Yeah, there was 6 of us.
6 of you in class. All right. That's good. Well, I know. I'm being facetious, but you guys are not up to speed on it. You just watched it Monday, right? I mean, come on.
Yeah, we started a little late, and it was just, we couldn't get the volume to work.
Oh, it's the worst. It's the worst. All right. I mean, I can keep making up stuff, but do you guys have a question? Can I give this quiz on Friday? I could give a quiz like it on Friday, probably. Yeah. Same concept, yeah. Sure. Here, tell you what. Let me project this and just talk through some strategies for different problems, okay? Sometimes it's just as important for me to tell you what you can't do, yeah? All right. So, let's see here, problem 128. How should we approach this problem? You did A? So A, I have, you have said, you ran Gram-Schmidt to find the orthonormal basis. Very good. Calculate the projection onto W of ABCD. Actually, that's what I just did with the 1, 2, 3 vector. Your answer should be a C of ABCDs in fractions and stuff, right? The point on W closest to 3, 3, 2, 4 would be the projection of 3, 3, 2, 4. So all you got to do is just take what you already did in part B and plug A equals to 3, B equals to 3, C equals to 2, D equals to 4. That should be the answer there. The next problem here, problem 129, we have a one-dimensional subspace of R2 by 2. 4-dimensional backdrop, right? That means that the perp to W is 3-dimensional. Find an orthonormal basis for W perp. Well, that better be 3-dimensional. This one here, I don't think you can do the perp thing. I mean, you can't do the null space of S transpose here because it's not column vectors. So you got to fall back on base principles, right? What does it take to be in the perp of W? Let's say ABCD is in the perp of W. What's that mean? It's perpendicular to, by the way, there's a theorem that says if you're perpendicular to the basis for a space, then that means you're perpendicular to the whole thing. So perpendicularity with respect to 0, 1, minus 1, 0 implies perpendicularity with respect to the span of 0, 1, minus 1, 0. So what does it take to be perpendicular, A, B, C, D, to be perpendicular to 0, 1, minus 1, 0? What does it take? A times 0 plus B times 1 plus C times minus 1 plus D times 0. That's the way the Frobenius product works. We just dot, it's just like you multiply corresponding entries of the matrix, right? So like, what I'm trying to say is the inner product of A, B, C, D was it 0, 1, minus 1, 0 is equal to what? It's equal to, I think, just B minus C, right? So what's the condition to be in the perp of W here? Yeah, just B equals C. What about A and D? No, not 0. I mean, possibly 0, but there's no condition on A and D. They're free. That's what we expect, though, because if this is one-dimensional, the perp should be three-dimensional, because remember, the direct sum of W and W perp is the whole thing. That's always our our conceptual guide is that theorem. W plus W perp is the whole thing. So if this is one-dimensional, whatever's perpendicular to it has to be three-dimensional. So you told me B equals C, because that has to be 0. And A and D are free. That makes sense. Basically, A, B, D, those are your three parameters for the three-dimensional. And then, okay, you got to find an orthonormal basis for W perp. So. So you maybe, I mean, putting this would give you something like, AD, BB. That would suggest basis like E11 and then 0, 1, 1, 0, 0, right? And then 0, 0, 0, 1. So your basis would be like E11 and E12 plus E21 and then E22. I think that's already orthogonal if you look at it. So you just have to normalize it, right? Because this matrix right, this is that matrix is in the basis, the natural basis for the W perp, but it's not normalized, right? It has length 2, square root of 2, so divide by square root of 2 to normalize it, right? All right, once you have that, to calculate the projection onto W perp, you do what? I mean, you can find a basis for W perp and take the dot product with respect to each part of the basis and do it that way. But, there's something else that might be. The projection onto W perp of a vector is equal to the orthogonal projection onto W of the vector. The orthogonal projection onto W perp of a vector is equal to the projection onto W of the vector. And we have these identities as well. The projection onto W of x plus the orthogonal projection onto W of x is equal to x. And likewise, so I don't know. I mean, there may be, if you think about it, lazier ways of calculating here than just directly doing what I already did. Just something to think about. Because it's pretty easy to calculate the projection onto W. How do you calculate the projection onto W? See, you just need to find a basis for W. the basis for W, orthonormal basis for W is just 1 over root 2, 0, 1, minus 1, 0. So to calculate the projection onto W, you just have to take the inner product of your matrix with that normalized 0, 1, minus 1, 0. That calculates the projection onto W. If you know the projection onto W of x, it's easy to calculate the orthogonal piece by x minus that, right? But that is this as well. Or you could just take the inner products with respect to your 3 basis vectors for W perp and put them together. I mean, it's the same thing. There's different ways of coming at it is my point, all right? And I think any questions about this? Probably should make sure I have those equations actually in the, yeah, they're in. Okay, so I think when you guys think through it, you should be able to do these. How would you find the matrix in W which is closest to 1, 1, minus 1, 2? That would be the what? But which one? This one or that one? Projection of W, right. That gives us the matrix in W, which is closest to that one. Yeah. Very good. Okay, good. Consider the plane P given by that and that, right? I say 1, 1, 1, 1 is not in this plane. Find the point in P which is closest to 1, 1, 1, 1. How would you do that? Here's my plan of action. Find a basis for the plane. Orthonormalize it. Calculate the projection of 1, 1, 1, 1 onto the plane. That's the closest point. Done. So you got to find a basis for the plane, right? That's a null space calculation because you have 2 equations. So you're really looking at the null space of 1, 1, 1, 1, 1, minus 1, minus 1, minus 1. Yeah. Next problem here, 131. Show that this defines an inner product. Okay, so what's that mean? You got to show it's with respect to, this is a real vector space, so that means it has to be bilinear. Right? It has to be linear in each spot. It has to be symmetric. So like inner product of f of x, g of x is the inner product of g of x, f of x. But that's like almost immediately obvious because you can multiply the functions one way or the other. So it's clear that it's symmetric. And also, if you have the inner product of f of x with f of x, you get the integral of f of x squared, right? If that's equal to 0, what does that mean? That means that the function f of x is identically 0 from 0 to 1, right? So if a polynomial is identically 0 from 0 to 1, does that mean it's a 0 polynomial? Can you have a polynomial which is identically 0 on some like closed interval and not be the 0 polynomial? Maybe this is something you haven't thought about before, but a polynomial is an example of an entire function. So calculus 2, we learn that if you have a function which is analytic, that is, it can be modeled by its Taylor series, right? Well, polynomials are such a function, right? So that means, in fact, I can expand the polynomial about any point, and that expansion must go for the whole thing. So if I take that polynomial and I expand it about any point between 0 and 1, then it's the Taylor series, which is generated as the 0 series. So that means if a polynomial is 0 on some open neighborhood of a point, it must be 0 everywhere. So it's not up for grabs. I mean, and that's why the axiom 4 for the inner product is fine for Rx. But the thing is, if you think about continuous real-valued functions, we no longer have that. We can't make that argument by Taylor's theorem. We don't know that all real functions are everywhere analytic. And in fact, there exist functions that look like this. I mentioned this in class. So they're identically 0. They're continuous everywhere. They're identically 0 between 0 and 1. So this would be the graph. So this would have, f of x with my definition equal to 0. The inner product of this function would be 0 with respect to that inner product, right? In problem 131. And yet, if this is the graph of the function, right, is that the 0 function? It is not. You can't construct such an example using polynomials alone. Polynomials cannot build that. You can't build a bump function from a polynomial. This is called a bump function. Okay, anyway. All right, so that gives you, I think I pretty much told you the answer for problem 131, why that fails to define an inner product. The reason it fails to define an inner product for continuous real valued functions is because you lose that. Just because the inner product is 0, it forces the vector that you're taking the inner product of itself with to be 0. The inner product of a vector with itself being 0 does not imply that the vector is 0. In this case, that vector is the bump function. So that's all right. Problem 132, this is just straight Gram-Schmidt, but you got to do the integrals, work through it. You'll get it. It's not bad. I think in one of the videos I posted, did I do it for -1 to 1? Did you guys watch that video? Somewhere in the videos I've linked, I do Gram-Schmidt algorithm on this 1x squared, but instead of the 0 to 1 integral, I do -1 to 1. This calculation is exactly the same as that. It's just the integral goes from -1 to 1 in my video, whereas this one goes from 0 to 1. But otherwise, it's the same thing. All right?
Would we know when to do, like, would it always just be explicitly stated, like, do maybe if it's 1 or 0?
Well, it's given here.
Okay, so will it always just be given?
It will be given.
Okay.
Yeah, because if a vector is normalized with respect to one integration inner product, it's not necessarily with respect to the other. There's a different notion of length, a slightly different notion. But this one here, you've already orthonormalized the first 3 of these in the previous problem, right? So I just tacked on one more vector. All you got to do is Gram-Schmidt on the 4th thing here to make this orthonormal. Or not, I guess. Is that what the problem is about? Sorry, I'm not sure that's even what the problem is. Oh no, I don't even need to do that. So the projection of EX onto this, so I'm just going to take basically dot products of, quote unquote dot products, I mean inner products of EX with the thing you created in the last problem to calculate the projection of the exponential function onto the set of possibly degenerate quadratics, P2R. Does that, I mean, I know you haven't worked it out yet, but that's a sketch of it anyway. All right, so I got about a minute left here. You just need to follow the instructions on problem 134. It's not that bad. You just got to work through it. Problem 135, I think I do it in the notes. If it's not exactly that, it's similar to that. This problem, I think I've sent you a link to a video with a very similar calculation. Yeah, a while ago now. Yeah. So the interesting thing here is that the answer to A and B will be different. Linearly independent with respect to real vector space structure and linearly independent with respect to complex vector space structure are different, because in a complex vector space you're allowed complex scalar multiplication, but in a real vector space you're not. So if one of the vectors is related to the other by like multiplication by I or something, it's probably the case that they're linearly independent in the real sense, but linearly dependent in the complex sense. And that's kind of what these two problems, that's the thing I'm trying to communicate with these two problems, is